Welcome back to Tachyon Signals. We often think of the universe expanding uniformly, galaxies drifting apart like specks on a stretching balloon. That cosmic expansion is happening, carrying everything away from everything else. But what if I told you that our part of the universe, including our own Milky Way, is being dragged sideways at over 2 million kilometers per hour towards something immense, hidden, and mysterious? It's a cosmic enigma known as the Great Attractor, a gravitational anomaly shaping the destiny of countless galaxies. In the vastness of space, everything is moving. Thanks to Edwin Hubble, we know the universe is expanding. Distant galaxies are receding from us, and the farther away they are, the faster they appear to move. This is the Hubble flow, the general outward rush driven by the expansion of spacetime itself. But in the 1970s, astronomers studying the cosmic microwave background radiation, the faint afterglow of the Big Bang, noticed something odd. The CMB provides a universal rest frame, a backdrop against which we can measure our true motion through space. They found our local group of galaxies, including the Milky Way and Andromeda, wasn't just moving away from distant objects as expected. It was also moving sideways relative to the CMB frame, at a staggering 600 kilometers per second. This wasn't random drift. Further studies in the 1980s, mapping the velocities of thousands of nearby galaxies, revealed a coordinated bulk flow. It wasn't just us. Entire clusters of galaxies across a vast region of space, spanning hundreds of millions of light-years, were all streaming in roughly the same direction, towards a point somewhere beyond the constellation Centaurus. It was like finding a massive river current within the gently expanding ocean of the cosmos. Something huge had to be pulling us. So what could exert such a tremendous gravitational influence? The obvious answer is mass. A lot of mass. Astronomers calculated that the source of this pull, dubbed the Great Attractor, must contain the mass equivalent of tens of thousands of Milky Way galaxies, concentrated in a relatively specific region of space, about 150 to 250 million light-years away. The problem was, when they looked in that direction with optical telescopes, they didn't see anything nearly massive enough to explain the observed motion. There were galaxies and clusters, yes, like the Norma cluster, but nothing that screamed, "I am the Great Attractor." The sheer scale of the required mass concentration just wasn't visible. This led to intense speculation. Was it an unbelievably huge single galaxy cluster hidden from view? Was it an exotic concentration of dark matter, the invisible stuff that makes up most of the universe's mass? Pinpointing the source became one of cosmology's great detective stories. How do you find something you can't directly see, whose presence is only revealed by the motion it induces in everything around it? Part of the difficulty in identifying the Great Attractor lies in its unfortunate location in the sky. It sits directly behind the plane of our own Milky Way galaxy, in a region astronomers call the Zone of Avoidance. Imagine trying to see a distant mountain range while standing in the middle of a dense, dusty forest. The trees and haze obscure your view. Similarly, the Milky Way's disk is packed with stars, gas, and vast clouds of interstellar dust. This material effectively blocks most visible light coming from objects behind it, making optical observations extremely challenging, if not impossible. For decades, this cosmic curtain hid the heart of the Great Attractor region. Astronomers knew something massive was lurking back there, pulling us towards it, but the details remained shrouded. It was like hearing a giant's footsteps approaching through thick fog. You know something big is there, but you can't make out its form. This observational hurdle forced scientists to get creative, turning to wavelengths of light that could better penetrate the galactic smog. How do you see through cosmic dust? You use light that dust doesn't easily block. While visible light gets scattered and absorbed, longer wavelengths like infrared and radio waves can pass through the Milky Way's plane much more easily. Astronomers began using powerful infrared telescopes and radio observatories to peer into the Zone of Avoidance. Surveys like the 2MASS infrared survey and radio observations of neutral hydrogen gas started to reveal the hidden structures. These surveys painstakingly mapped out galaxies previously obscured by the Milky Way's dust. What they found wasn't one single colossal object, but a significant concentration of galaxies, including several massive galaxy clusters like the Norma cluster, Abell 3627, right in the suspected heart of the Great Attractor region. The Norma cluster in particular is incredibly massive, perhaps 1,000 trillion times the mass of our Sun. While still not quite enough on its own to account for the entire pull, its discovery confirmed that a major mass concentration did indeed exist, where the bulk flow seemed to be pointing. The veil was lifting. The picture became much clearer in 2014 with the work of Brent Tully and his colleagues. They developed a new way to define large-scale structures in the universe, not just by the distribution of galaxies, but by their motions, specifically by mapping the gravitational flows. Think of it like mapping watersheds on Earth, where rain flows downhill towards rivers and eventually collects in ocean basins. Tully's team mapped the peculiar velocities of galaxies, tracing their paths along the gravitational gradients of the cosmic web. They defined a supercluster as a region of space where all the gravitational flow lines converge towards a common center. Using this method, they defined our home supercluster, naming it Laniakea, a Hawaiian word meaning immense heaven. Laniakea is vast, stretching over 520 million light-years and containing the mass of about 100 quadrillion suns, spread across roughly 100,000 galaxies, including our own Milky Way. And crucially, the gravitational center of this enormous structure, the point towards which everything within Laniakea is flowing, lies precisely in the direction of that mysterious Great Attractor region, encompassing the Norma cluster and its neighbors. The Great Attractor isn't necessarily a single object, but the gravitational focal point, the basin, of our local supercluster. We aren't just being pulled towards it, we are part of the structure defined by it. Just as the mystery of the Great Attractor seemed to be resolving into the Laniakea supercluster's gravitational center, another twist emerged. While the mass concentration in the Great Attractor region, like the Norma cluster, is significant, detailed analysis of the cosmic flows suggested it still couldn't fully account for the high speed of our local group and other galaxies. There seemed to be an additional, even larger pull, coming from beyond the Great Attractor. Peering even deeper into space beyond the Great Attractor region and still partially obscured by the Zone of Avoidance, astronomers found something even more substantial: the Shapley Supercluster. Located about 650 million light-years away, Shapley is a truly colossal concentration of galaxy clusters, one of the most massive structures known in the nearby universe. It acts like an even bigger gravitational mountain range further down the cosmic river. So, the picture now is more complex. Our motion is likely a result of being pulled towards the gravitational center of Laniakea, the Great Attractor region, while simultaneously being pulled by the more distant but incredibly massive Shapley Supercluster. It's a gravitational tug-of-war on a cosmic scale, with Laniakea defining our local flow, and Shapley exerting a powerful influence from afar. Understanding the Great Attractor, Laniakea and Shapley is about more than just mapping our local cosmic neighborhood. It's about understanding the large-scale structure of the universe itself. These superclusters are nodes within the vast cosmic web, an intricate network of galaxy filaments, clusters, and vast empty voids that permeates the cosmos. This structure originated from tiny quantum fluctuations in the very early universe, amplified by gravity over billions of years. Dark matter, the invisible scaffolding of the universe, played a crucial role, collapsing first and drawing ordinary matter into these web-like patterns. The flows we observe, like our motion towards the Great Attractor region, are galaxies following the gravitational pathways laid down by this underlying structure. Studying these flows helps us map the distribution of both visible matter, galaxies, and invisible dark matter. It also allows us to test our models of cosmology, gravity, and the influence of dark energy, the mysterious force accelerating the universe's expansion. Future telescopes like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope are specifically designed to map the large-scale structure and galaxy motions with unprecedented precision, promising to shed even more light on these cosmic giants and the forces shaping our universe's evolution. So, the Great Attractor isn't a single terrifying object swallowing galaxies whole. Instead, it represents a gravitational focal point, the center of our home supercluster, Laniakea, a vast cosmic watershed guiding the flow of tens of thousands of galaxies, including our own Milky Way. Its pull is real, a consequence of the immense concentration of mass, including galaxy clusters like Norma, located within that region. Yet, the story is even grander, with the more distant Shapley Supercluster also playing a significant role in the cosmic currents. What began as a puzzling anomaly in galaxy velocities has led us to map our place within the immense structure of the universe, revealing the intricate dance of gravity shaping the cosmos on the grandest scales. The journey to fully understand these structures and the forces driving them continues. Thank you for joining us on Tachyon Signals as we explore the mysteries of the cosmos.